Sample solution of some related rates problems with trig functions. In this video, we'll walk through the solution of a related rate problem illustrated below. Example 1. A 27-foot ladder leans against an 8-foot wall with its top projecting over the wall. The foot of the ladder is being pulled away from the wall at the rate of 5 feet per second. How fast is the angle changing when the foot of the ladder is 6 feet from the wall? First, as always, we should draw a picture and define our variables. Here, the length of the ladder will be L, the height of the wall will be H, the distance of the foot of the ladder from the wall will be X, and the angle between the ladder and the ground will be theta. Next, we need to decode the text of the problem. In word problems, the first thing to identify is the thing you're actually looking for. Here, we're asked, how fast is the angle changing? How fast something changes is the time derivative, so we're looking for d theta dt. We're given how fast the horizontal distance is changing, that is, dx dt, which is 5. It's positive because the foot is getting further away from the wall, so x must be increasing. The particular moment we're interested in has x equal to 6. We need to connect d theta dt to dx dt, so we need to connect theta to x. Luckily, we can do that through the triangle. Tangent of theta is h over x, which we can solve for x in order to make the derivatives easier, making x equal to h cotan theta. Now we can take the derivatives of both sides. dx dt is ddt of h cotan theta, but h is a constant, so it comes outside. Cotan of theta is a function of theta, not t, so this is essentially a chain rule. We take the derivative with respect to theta, and then pay for the chain rule by tacking on the derivative of theta with respect to t, which is what we want anyway. The derivative of cotan theta with respect to theta is minus cosecant squared of theta. You could actually stop here and figure out the cosecant, but it also can be polished a little bit more by recalling the Pythagorean identity for cotan and cosecant. This allows us to eliminate theta entirely and get a relatively straightforward relation depending only on x and on h, of course. Now we solve for what we want, which remember was d theta dt, and we plug in the values of the moment we were asked about. In this case, we see that the ladder is rotating clockwise, because d theta dt is negative, and at a rate of 0.4 radians per second. We can use the same setup to answer different questions. For example, we can find the greatest horizontal distance that the ladder projects over the wall. In this animation, that would be the length of the dashed orange line. We'll need a drawing again, of course, and we'll use this sketch. Here, L, H, and theta have the same meaning as before. The overhang distance is S, while P is the length of the part of the ladder over the wall, and Q is the length of the part below the wall. Our goal is to find the maximum of S. We'll do that by finding an expression for S as a function of theta and setting that derivative to 0. Using the upper triangle, we can relate S to P and theta. Using the lower triangle, we can relate H to Q and theta. And here's the key bit. P and Q are the lengths of the pieces of the ladder above and below the wall, so together they must add to the total length of the ladder, which is L. Now we can substitute and solve for S. Everything on the right-hand side is a constant except for theta. Since we have S as a function of theta, we can just take the derivative. For an extremum, the first derivative must be 0. Either cosecant theta is 0, which never happens, or the other factor is 0, implying that sine of theta equals the cube root of h over L, which is 2/3 for this problem. We're in quadrant 1, so this is unique. We don't actually need theta, only its cosine and cotangent. Now, at last, we can just plug into the equation for S, and see that the maximum distance would be 5√5 feet. Here's a graph of S as a function of theta, with the discovered value of theta marked. Note that it's the maximum. Also note that this appears to go negative because there's an angle where the ladder's top has lost contact with the wall. After that, the physical model doesn't apply, so our function doesn't apply either.